start talking. As we walk through life, we run into numbers that look significant. Is it working? Do you recognize that number? 3.1415 and so on. So what is it? Huh? Yeah, this would have been pi if that digit had been 7 instead of 4. And what about this 007? Everyone knows 007. And that's, of course, James Bond, but it turns out to be the surface tension of water at 25 degrees, very nice temperature in Park City today, in the metric units joules per meter squared, or if you like, Newton per meter. Yeah? So this is surface tension between water and vacuum, if you like, or more or less surface tension between water and air. And knowing that number, you can figure out lots and lots of interesting phenomena in life. 0.07, that's James Bond. And sometimes you run into numbers that look familiar, which you know is significant, but you cannot quite place. For example, when I saw this number a few days ago, I knew that this rang a bell, and it appeared sometime in important junctures in my life, but I couldn't place it. So I racked my brain, I mobilized my entire scientific education, I tried to do orders of magnitude on the backs of envelopes and so on. So I couldn't really place it. And finally this morning I thought, yes, eureka, I know what it is. This is the fax number of the Institute for Advanced Study in Princeton. And now the leitmotif of this talk is going to be, the really running current, is going to be this number 2.5. 2.5, I'd like to tell you, ladies and gentlemen, boys and girls, that it is a number exactly between 2 and 3. And this is the dimension, effective dimension in which surface, membrane, and anything that is spread out thin in space, for example, a sheet of paper, evolves and continues to surprise us. Okay, so I shall start with one magic trick. Main camera, please. Here is a coaster that they brought, which is circular, and then a piece of paper on which I drew the hole. And when I fold it like this, I can pass this coaster through the hole. Okay, it's passing through, you can pass backwards and so on. And it goes both ways. I haven't started cheating yet, it's really passing. But if I put one next to the other, clearly, the diameter of this disk is larger than the diagonal of this hole. I didn't stretch, let alone tear. What is going on? And yet, you can actually pass one through the other. It is actually going through, you can see. How come something larger passes through something smaller? Okay, so this is really the first gambit, opening gambit. Because you look like a nice set of people, well, most of you do. I'm going to reveal the secret for free. I usually pass around the hat at this moment. And you see, this is a hole, which is, always the camera, please, not back. Thank you. So this is a hole that I made. And if I fold it like this, the maximum gap that I can take advantage of is this one, which used to be the diagonal of this square. Okay, but that's not all I do. I grab this and then start twisting the whole paper like so. And in doing so, I don't know if you can see it on the camera, the paper starts lifting in the third dimension. It escapes from the 2D into the ambient third dimension. And in doing so, I can align those two sides along a single line and then squash. The gap that I have created there is no longer the diagonal, but rather the sum of the two sides. And if you remember Pythagoras, I've gained a factor of square root of 2, 40% or more. So I'm passing the hole through this hole, which is a little larger. The secret to success, therefore, was to make a hole whose diagonal, square hole, whose diagonal is shorter than the diameter, but whose sum of two sides is longer. And so, slide, please. What was impossible becomes possible because I escaped in the third dimension. And what is going on is that if you are really in the straight jacket, if you like, in the confined space of 2D, but because you took advantage of the ambient dimension, and because my sheet of paper can actually move in the third dimension, this visibly impossible thing became possible. Okay. Do you recognize this portrait? He's one of the most romantic figures in the history of mathematics. He looks rather tragic. You know who that is. That's Évariste Galois, who died at the young age of 20. And you might think, well, Tadashi cannot do arithmetic because if you look at the birth date and the death date and the 32 subtracted, you subtract 11, it becomes 21. But he died shortly before his 21st birthday. He left, of course, a gigantic legacy for us to chew on. And one of the things that least of these things that he allowed us to solve is a classical Greek problem, which asks, with ruler and compass, straight edge and compass alone, can you divide a given angle into 3 equal parts? You have experience, all of you from high school, of being given an angle and bisecting it, that is dividing into 2 parts. It's very easy. Yeah, you do this, do this, do this. But can you do it in 3 equal parts, trisection of an angle? And of course, people have tried and so on. But one of the first things that you can learn when you go to college and then you study Galois theory or some field extension and so on is that no, there do exist angles that you cannot divide into 3 equal parts. For example, an angle which looks innocuous like 60 degrees is impossible to trisect with rule and compass alone. By the way, there do exist, of course, angles that can be trisected. For example, flat angle, 180 degrees, it's very easy. But the 60 cannot be trisected. In other words, 20-degree angle cannot be constructed with rule and compass alone. However, there is a traditional Japanese art which goes back about 1,000 years, because that's when paper started being commonly used in Japan, of origami. Ori means to fold, oru, and kami means paper, so folding of paper, paper folding. And this is a very beautiful thing. And with origami, it turns out that you can trisect an arbitrary angle. So I'd like to show you how that is done. Let's revise how to bisect an angle with origami. Say that you have an angle, your given angle, given as corner of a sheet of paper. Yes. Usually the corner of a sheet of paper is always 90 degrees. But say that you have a sheet of paper whose corner is your given angle, okay? How do you bisect that? Well, nothing is simpler. You just fold the paper over, and then you align the edges. And when the edge is aligned, you just crease that little fold. And when you open, you have a beautiful divider, which is coming out of the angle, that corner. And that is the bisector of the angle, obviously. How do you trisect? It's no harder. You just fold, but you overshoot, and then fold back. And then you have those 2 edges on this side and that side. And you start aligning them. You just negotiate with your hands. Yes, that's actually key. You negotiate with your hands. You are choosing a parameter from an infinite continuous family of parameters, and that's the strength of origami, if you like. And when they are nicely aligned, you just crease both, and when you open, you have 2 beautiful lines coming out, and those are the trisectors of your angle. And for n section, division into n parts, you just go back and forth, you create something like a covering space with n sheets and so on, and you just negotiate the size, and you crease, and you open, and you can do for all n. And this miracle was achieved because you have the power and the elegance of origami. Do you know this person, next person? No less famous in performance. And he looks rather grumpy, and that's, of course, Carl Friedrich Gauss. And he, too, is a giant, and he really stands at the junction between the 18th and 19th century, and really modern mathematics starts from Gauss, and he seeded lots of them, and many of those were imaginatively extended by Riemann and so on. So one of the things that he allows us to answer very easily nowadays is another classical Greek problem. For which n can you construct, always with rule and compass alone, a regular polygon of n size, regular n-gon? For example, there I show you a construction of a regular 3-gon that is known as equilateral triangle. You just draw a segment, and you plant a pivot of a compass on one side, and then on the other side, and those 2 arcs intersect in a point, and that's the vertex of the equilateral triangle. So many n-gons can be constructed. So which n are possible? Well, it turns out you can prove after Gauss that not all n are possible, and in fact, n must look like a very, very special form. And it has to be a power of 2. That's kind of cosmetic. I'll come to that. But the essential information is contained in the product of distinct primes. Those are primes 2 to 2 to small n plus 1. What a funky looking thing. These are called Fermat primes. And if you plug into small n various numbers, 1, 2, 3, 4, 1, you get a sequence which is a little mysterious. 1, 3, 5, 15, 17, 51, and so on. I listed them. And those bold-faced ones, 3, 5, 17, 257, these are primes. Those are Fermat primes. And if you have any product of those Fermat primes and power of 2, then you can construct that n-gon, and it's if and only if, okay? Power of 2 is easy because once you have constructed some n-gon, you can always divide each of the sides by in 2, so you can always double number size, so that's really cheap. But the really beautiful and rather mysterious statement is that thing. Well, you're probably beginning to suspect that with origami, you can do all n. Okay, so camera, please. I'm going to show you how to construct a regular n-gon, a regular 5-gon first, okay? Now, 5 was one of the Fermat primes, so it's not that impressive, but this will illustrate what you do in all generality. So I'm going to do it for 5. What you do is to take a strip of paper and tie the simplest possible knot that you can imagine, this like so. And having tied this knot, I tighten it and then flatten it, tighten and flatten it, and I keep negotiating. This is a continuous search in the space of parameters. And eventually, I get a completely tight knot in the middle, which is flat. And when I achieve this, I get this configuration. Now, there are pieces sticking out which are irrelevant, so I'm going to throw this away to show you what's in the middle. Okay? And when I throw away these pieces, what you get in the middle is a perfect regular pentagon. I didn't have to think at all. You shouldn't applaud me. Oh, you can applaud, but you should applaud nature, because nature took over. I didn't do anything. Yeah? Yeah. Regular pentagon. So it is a relatively painless and rather actually essentially pleasant, I would say, exercise to prove, just by drawing a diagram, that you get a regular pentagon if you do this. So something to do after dinner. Now, that's regular pentagon 5-gon. Okay? So how do you do for all n? First of all, it's enough to do it for n equal odd, because as I explained, once you have an n-gon, you can always double. So odd gons, I'm going to construct odd gons. How do you do this? Well, when I did this operation, I took a strip of paper and made the simplest possible knot. So I made one pass of the strip through itself, as it were. Okay? One pass resulted at the end in 5-gon. If I make a knot with 2 passes, how? I'll show you a diagram in a moment, but the 2 passes, the next simplest knot, and then flatten and tighten, you get the regular 7-gon. 3 passes, 9-gon. 4 passes, 11-gon, and so on. So you can actually do this in general. Can I have the slide, please? Okay. The picture is like this. In the right part, I draw the regular 5-gon, and the 7-gon is there. The best way to visualize how to make this knot is as follows. Imagine that the regular n-gon, regular odd-gon, is already constructed. For example, look at 7. And then think of, of a ray of light that comes in, and the inside of that regular 7-gon is made of mirror. And then it just bounces off, boom, 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 eventually it goes out, okay? And that order of boom, 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 boom tells you which piece of the paper goes above and which goes below in that order. And then you just tighten it, okay? Now, that's nice, hunky-dory. So 1 pass gives you n equal 5, 2 passes n equal 7, and so on, so on. But there's one odd-gon missing, regular 3-gon. Yeah, n equals 3. So if 1 pass gives you n equals 5 and 2 passes n equals 7 and so on, how many passes do you have to make in order to have n equals 3? Hey? Huh? 0 pass, and that's that. So you come in and you try to make a knot, but you don't manage and you go out. And then in that corner, you have a regular 3-gon that is an equilateral triangle happening. And as I explained, bisection is for free, so you can access any regular n, okay, with origami. Now, I would like to show you something and give you a present today, okay? A present is usually an object which is heavy, which costs money, which is breakable, and when you go through airport securities, you get into trouble. But the present that I brought you for today is a phenomenon, not an object. It's a mathematical phenomenon also. So it weighs exactly 0 grams, costs you 0 cents, and it's unbreakable. You can keep actually sharing with people, and the more you share, the richer you become. And when you go through airport securities, they're no wiser about this. So this is, what I would like to show you is a phenomenon. Now, a lion has been folded by me, and then when I unfold it, this is the folding pattern that you see on the sheet of paper. Don't pay too much attention on the blue and red and so on. These are ridge and valley folds. But what I would like to call your attention to is that look at some of the vertices, and then where edges are meeting, okay? So points where the lines are meeting. So many of them have 4 edges meeting, that is, vertex of degree of valency 4. And some of these have 6 edges meeting, and some of them 8 edges meeting. It turns out that if you take a sheet of paper and fold anything, but at the end of the day, you squash it onto the plane, and then you open. So this is the typical, no, not the slide, please. Always on the side. Unless otherwise explicitly instructed slide or the camera. Okay, when I squash it, okay, so this is the type of origami which is flattable, if you like, then every vertex of the folding pattern has an even degree, an even number of edges coming in. This is not difficult to prove, so I'm going to ask you to believe it, okay? But it's actually not too, so for the experts, I can say, when I flatten it, I create something like a singular covering space, and which has the pattern of front, back, and that forces basically the parity. But anyway, so that's what it is. So the simplest case is shown in the low corner. You have 4 angles that are coming out, vertex of degree 4, and you have angles around them of that. Now, camera, please. So let's see what we can do. The simplest kind of fold that you see in the world and which you use every day is what is called a square fold by the origamists. You do this, and you do that. And then what you see is I'm going to trace the edges, that, okay? And then so all the angles are 90 degrees. Okay, nothing is simpler than that. On the other hand, that was a bit too careful. If you do things at random, what you're going to get is something like this. I didn't pay any attention to what I was doing. And I'll trace the 4 edges that come into that vertex, and that. 2 of these are mountain folds, and 1 of them is a ridge fold, or the other way around. That's, of course, that's part of physics. And we have 4 sectors, 4 angles. Now, I'm going to name those angles. And let's see, the camera is there, so I'm going to write alpha, beta, and gamma, and delta. Have you noticed that I just wrote the Greek alphabets upside down? You could be applauding at this stage, but anyway. Okay, well, thank you. I love spontaneity, good. So those angles. Now, it turns out that those angles cannot be arbitrary if they resulted from folding a sheet of paper, from origami, by squashing, as I have just done. Yeah? Okay. So what are the conditions? Can I have the camera, please? No camera, the slide, please, thank you. So the first of those conditions is that those angles must add up to 360 degrees. You wish that you said it, but I said it first. Okay. So that's the, yeah. But the other condition is rather remarkable. It says that the opposing pairs of angles, alpha and gamma on the one hand, and beta and delta on the other hand, must have the same sum. Can we have the camera, please? So this plus this equals this plus this. Note that in the 90-degree square folding pattern, that's certainly true. Yeah? But it's true here, okay? So I'd like to prove to you how this is really true, okay? It's a phenomenon that you can take home. I'm going to give you a proof. In order to prove this, let's go back to how this was created in the first place. It was like so, okay? What is going on here? Oh, here. Excuse me. Here, okay? That's that. So that's alpha, right? But seen from that side, that's alpha also, but that's equals beta plus delta. Oops, I overcounted gamma. Did you understand that? No, I didn't. So let's do that again. So this is alpha, yes? And if you turn over, that entire angle is alpha. But alpha consists of the overlapping beta and delta, yes? And the overlap is gamma. So alpha equals beta plus delta minus gamma, which is the same thing as that QED. Can we have the slide, please? Yeah. So that's it. And in particular, a configuration like the one that I depicted there is impossible to achieve by origami. by folding a sheet of paper because the sum of that small sector with a huge sector is far too large compared with the sum of the other two. However clever you are, you cannot do this. That's an obstruction. And in general, I told you that there are even number of angles coming in. So let's say that angles are alpha 1, alpha 2 through alpha 2n. These angles, or if you like, these positive real numbers, are realizable by crumpling a sheet of paper. By crumpling, I mean folding it like origami and squashing it. If and only if, that's a necessary and sufficient condition, that's a theorem. First of all, they add up to 360 degrees, thank you very much. But the more important and less trivial condition is that they're alternating sum, not the sum, alternate sum. That is, alpha 1 minus alpha 2 plus alpha 3 minus alpha 4 plus alpha plus minus closes to 0. I say close because this is kind of the discretized version of a homological condition. Yeah? So it's a closure as in closed form and so on. But that is the necessary sufficient condition. And the for case can be written like this because instead of alpha plus gamma equals beta plus delta, I could have written it as alpha minus beta plus gamma minus delta equals 0. The proof is exactly the same. So if you give me, for example, Rafe gives me a bunch of positive real numbers, and they say, well, realize them by folding a sheet of paper. Well, what do I do? First of all, I have to check that they add up to 360 degrees, but then Rafe is rather mischievous, so he's going to give them in some deranged order, right? So I have to actually arrange them in the correct order. So what I'm saying is that the given order might not achieve this 0 condition, but there might be a permutation whose alternating sum becomes 0. If that's the case, what do I do? Here's the proof. Really the proof and demonstration you want. You take the largest of those numbers, and then you start folding the paper back and forth, back and forth, back and forth in that order, cyclic order. And when I run out of the supply of angles, I know I exactly close because of that 0 condition. And then what I do is just crease the edges and open, and you have all those beautiful lines coming out of the vertex, and that's the realization of your angles. Okay, good. So you have now a present for you. We have been so far playing with geometry and mathematics, pure mathematics if you like. We'll transit gently to physics now. And from physics, we'll go on and expand our field of investigation to engineering, physiology, and what have you, more things, and even medical application later on. And we really have to expand our view, our vision of the universe, because the phenomena that we are talking about are all over the place. Yeah, from the largest scale to the small scale. For example, in the top left corner, I depicted a picture of a paper that is called Mino paper from Japan, from the west of Japan. And that paper is manufactured in more or less in the following fashion. So you take a sheet of paper, traditional Japanese manufacturing, and then when you do it, you wet it first. And then you take a sliced persimmon, you know persimmon fruit? This is the national fruit of Japan, kaki. And then you start rubbing the paper like this, scrubbing it. And this scrubbing sort of intermeshes some of the fibers in an intricate pattern. And when you have rubbed the persimmon all over the place, you let it dry. And after it has dried, you wet it again, and you start scrubbing in various other directions. You keep repeating this process. And at the end, what emerges is that there is a version of paper which is so robust, which is also flexible, but so strong that you can make, for example, clothing, you can make a purse, you can make bags, you can even make shoes out of this paper. And all those sort of meshes and so on, interesting sort of structure is happening on a scale of less than a millimeter, so it's really small. In the top right corner, you see my friend and one of the nicest animals, and you can see the elephant's trunk is lined with lots and lots of wrinkles. They are the best of biomechanical and thermal reasons why nature takes advantage, living nature takes advantage of those, and that's on the scale of, let's say, centimeter to meter, on the human scale, on our scale, right? Okay. And in the lower right corner, you see the backbone of Latin America, South America. So that's the Andes, the majestic mountain range, which extends over 5,000 kilometers. And how did this come to be? Answer, because nature plays origami on that scale. You see, there is the plate on the Pacific side, this is called Nazca plate, which is pressing against the Latin American plate. And so what happens, don't switch, if you press something, as you saw, this rises because it wants to escape in the third dimension. And this is exactly what the Andes is. By the way, I'd like to make a digression. You know that the Amazon, which is the greatest river in terms of water flux in the world, is flowing into the Atlantic. Do you know that it used to flow into the Pacific? It used to. And so geological records show this. And not long ago, Andes started rising and then tilted the entire continent in the other direction, and water started flowing in the other direction. Anyway, so nature plays origami there on the scale of kilometers, nay, thousands of kilometers, so huge scale. And across all these scales, you might have some of those origamis designed by humans, or some of these randomly generated. And depending on those nuances, it has the same phenomenon has many different names. The most designed and deliberate ones are called origami, and on the other side, random ones called crumpling. And in the middle, there is the constitutive unit of all this is called buckling. You know what buckling is? So I don't know, maybe I should show it from that camera, the alternative camera, thank you. So this is a little strut, and if I compress the two ends vertically, for a while, it just wants to shrink elastically. But at some point, at critical load, it cannot take the load anymore, boom, it deflects sideways, large deflection. That's called buckling, and it was perfectly analyzed by Euler. So this kind of thing is the basic mechanics, if you like, behind origami, behind folding. We shall come back to that when we do the buckling in 2D and higher dimensional versions. Can we have this slide, please? Okay, so the challenge is, across all this huge range of scales and this great diversity of phenomena, can we make science out of this? Can we extract some laws of nature? For example, even in this case of random crumpling, that looks like a randomly crumpled sheet of paper for the good reason that it is actually a randomly crumpled sheet of paper. And can you see something in there? Let me rephrase the question. What are we saying? So if you ask an artist to draw a crumpled sheet of paper, you find that there are very, very few artists who can do a creditable job. All that they can draw doesn't look like a crumpled sheet of paper. Whereas you, who have been living in this universe for long enough, some of us longer than others, can see and recognize a crumpled sheet of paper. It looks like one. It doesn't look like one. In other words, there are things that we're seeing subconsciously which kind of have the conditions for obstructions and so on, which make a crumpled sheet of paper among this space of all the embedded graphs on the plane. Yeah? Embedded because metric properties are very important. So just not the combinatorial information, but also, so among all these sort of pictures that you can draw, what makes something a result of a crumpled sheet of paper? That's what I would like to uncover. Okay. So what I would like to do is to go into that wider world. Do you recognize this person, the third person? He's less famous than the previous two, and he's no less important in some sense. That's Simon Denis Poisson. He looks much happier than the previous two. And if you study sciences, for example, you can have Poisson's equation in potential theory, Poisson distribution in probability, Poisson bracket in analytical mechanics, and Poisson this, Poisson that. And what I would like to show you today is to teach you half of the theory of elasticity. This is a branch of theoretical physics. Half of the theory of elasticity in 45 seconds. Here we go. So take a piece of material and squeeze it in one direction. What do you think happens? Well, it will bulge out in the transverse direction. Yeah? And if you stretch it in one direction, it will reduce its girth. It will tuck in its belly in the transverse direction. How much it responds in the transverse direction per how much you squeezed in or out, that ratio, strictly speaking, you take the derivative, is called a Poisson ratio. Okay? So that's the bulge per squeeze. For example, if you have an incompressible material, you just squeeze, and there are two other directions into which you can escape. So half and half against -1, that gives you half as Poisson ratio. Why am I putting trace equal to 0? Because trace is the derivative of the determinant. But anyway, so that's what it is. Now, this is a fundamental quantity, fundamental material, if you like, characteristic of anything. But for such a fundamental thing, there is very little consensus on its notation in the literature. And so many people, including Landau Lifshitz, whom I shall cite in a moment, calls it sigma. Some other people who should know better call it pi, oh my God. Or some people call it lambda. That's very bad because that should be the Lamé constant. Some people should call it p, God forbid, and so on. So huge variety of just chaos of notation. Now, after many years of very deep thought and maybe standing under waterfall in Japan. And so I finally came up with a God-given, or rather at least Tadashi-given, canonical, absolutely canonical notation for Poisson ratio. Okay? And it is this. It's alpha with a dot, yeah? And with Metafont, it's very easy to make this. So in the future, if you are going to use Poisson ratio in your work, and please use this notation, in 200 years' time, I want to be remembered in the history of science as the person who finally found the right notation for Poisson ratio. Let's train our intuition by doing this. Say that you have a unit cell, such as that, and then it's just basically made of rigid rods, which are green, and universal joints, yeah, those black points, and so they can all flex and so on. Now, if you squeeze that unit cell in the middle left corner, along the blue arrows, you can see that it's going to respond by expanding along the red arrows, okay? So that's Poisson ratio behavior, and you can already assemble that into a structure, into some kind of mesh, and this is already useful. For example, if you design a dress like this, when you stretch the dress, it hugs you, and tightly and so on. This has been used. So that's positive Poisson. You can make the unit cell hexagonal. So then you have a honeycomb pattern, and then that has an interesting response, and so on and so on. The truth of the matter is that the Poisson ratio varies a lot from material to material, structure to structure, but there is one belief that has been prevalent throughout the science, throughout the field, throughout the industry, which is the belief that the Poisson ratio should always be positive, yeah? Greater than or equal to 0, strictly positive. But there do exist structures and materials which seem to have almost 0 Poisson ratio. Take the spring, for example. This is very, very direction dependent, but take the spring and try to compress the spring along its length. Well, it doesn't seem to be getting any fatter in the transverse direction, but actually, if you look really carefully, it is getting fatter. So you see the Poisson ratio is almost 0, but nonetheless, really strictly speaking, it's positive, okay? So there's a belief, and so it's really absurd to believe that there exist things that upon being compressed in one direction, it also shrinks in all the other directions and so on. So this belief is supported by the greatest authorities. This is Landau Lifshitz. So Landau, as you know, was a great Russian physicist who created single-handedly a huge and powerful school of theoretical physics in Moscow, which really marked, in some sense, the style of theoretical physics in the second half of the 20th century. And here in that cartoon, there is depicted Landau preaching to his students. They all have donkey ears and wearing glasses and saying, "Thou skazal," the master said, "Thou skazal." Now, the Landau, together with his first student, Lifshitz, left for us a monumental series of books called Course of Theoretical Physics. If you go into the office of any practicing theoretical physics in the world, I really mean the world, you'll see several volumes of Landau Lifshitz. It's that famous and that important. I quote and I use no book more than Landau Lifshitz in my life also. And the volume 7 is devoted to theory of elasticity. I don't know why I took the French edition, because that's my workhorse in my office. But anyway, in that book, there is a passage discussing Poisson ratio and a footnote. Yeah? And I sort of highlighted that footnote. It's too small to read, so I'm going to read and translate at the same time. It says, after introducing Poisson ratio, actually, the Poisson ratio varies only between 0 and 1/2 for isotropic material. We don't know of any body in nature for which the Poisson ratio, sigma, that's their notation. Yeah? Do you know a better notation for Poisson ratio? Oh, thank you. So this is alpha with the dot. So Poisson ratio would be negative, that is, which would bulge out while being stretched. That's what Landau Lifshitz says. Okay, the greatest of authorities. Faced with that authority, it becomes very tempting to design negative Poisson ratio structures, and once you start, it's actually very easy. So, on various trips along Eurostar, I designed those things. Instead of taking an hexagonal unit cell, take another hexagonal unit cell, but now a concave one. In the field, we talk about the reentrant corners. So if you have a gadget like that, and then you squeeze that gadget along the blue arrows, you can see that it also compresses along the red arrows. Okay? That's negative Poisson behavior. You can assemble them into some structure, and that actually has a very, very interesting property. That was kind of translation, but you can do it rotationally too. Here you have an innocuous-looking bunch of squares, but actually these are all jointed in a funny pattern. Here's a halfway diagram. When I start pulling some of the points apart, those squares, which are jointed at the corners, turn in alternation, left, right, and then they dance and expand. Okay? You can do that with not squares, but also triangles and so on. And there are 3D versions of these. So these are all Poisson ratio because you stretch in one direction, they start expanding all the other directions on average. Okay. So the truth of the matter is that for isotropic material, isotropic means that it doesn't depend on directions. We'll come back to anisotropic later on. For isotropic materials, the Poisson ratio is not, contrary to what people have been believing, between 0 and 1/2. It is between actually -1 and 1/2. The lower bound is lower. It's in the negative region. Now, those bounds have some physical interpretation. For example, the upper bound 1/2 is the incompressible limit, not to be confused with the incomprehensible limit. So what is it? Well, as I explained, for a 3D material, when you have an incompressible material, that means that it doesn't want to change its volume. Well, if you squeeze in one direction by unit, it has to escape in 2 remaining directions, so 1/2 and 1/2 will do it. So in, for example, d-dimensional space, it's going to be 1 over d minus 1. Okay. What about the lower bound? Yeah, -1. That is the unshearable limit. Do you know what shear is? So what you do is that you take, say, a deck of cards, playing cards, and it's a rectangle, seen from the side. You put your palms at the top and the bottom, and while keeping them parallel, you just slide them against each other. And then the rectangle becomes a parallelogram. Okay? That motion, that strain is called shearing. Okay? So it turns out that if Poisson ratio becomes negative, as it approaches -1, the material becomes less and less shearable, and -1, it becomes absolutely unshearable. Okay? I'm going to explain, and this has to do with what is called the polar decomposition of any endomorphism. So any square matrix can be written as a product of orthogonal matrix and symmetric matrix. Well, that's easy to prove in linear algebra, but it's even better to see it in picture. Let's say that you have this brown square, which I want to shear into that green parallelogram, okay? I can do it in 2 stages. First, take the square and stretch it along the red arrows and compress it along the blue arrows, okay? That makes a losange or the rhombus, okay? Having done that deformation, you just rotate the whole thing, stonk in place, and the result up to high order infinitesimal is indistinguishable from the result of shearing, okay? Now, if the Poisson ratio is negative, that first stage, that symmetric matrix stage, becomes really hard because when you try to stretch it along the red arrows, it wants to also stretch along the blue arrows. It will resist being compressed. So it becomes harder and harder, and at -1, it becomes absolutely impossible. So that's the theorem. The bounds are for isotropic material -1 and +1/2. Now let's use that. This person is still alive, thank goodness. Mr. Miura, he's one of the most imaginative engineers, aeronautical engineers in history. And in the 1970s, he introduced this beautiful fold called Miura Ori. Ori, as I explained, is fold. Okay? And so, what is Miura Ori? Can we have the camera, please? You know how annoying it is to fold a roadmap. Oh, but wait a minute. So I said fold a roadmap, but maps used to be made of paper. Do you know that? I mean, I see lots of young people here. It's not like this. Paper, yeah? And paper used to make maps, maps. So you opened and closed like this. You didn't swipe. You know this? But anyway, so when you are opening a roadmap, it was okay, you open, and then you want to know how to go from Salt Lake City to Park City, and you open. But when you try to close it, it never falls back the right way. It starts sort of creasing in some strange places, and it sort of goes backward, and then you make a hole, and you go crazy, and next thing you know, your car is in a tree because you're no longer driving. And this happens because there's too many degrees of freedom in this fold, okay? Now, Miura Ori is a remarkable thing. It is this one. So I brought this, a certain fold. And in order to fold it back, all I have to do is just to press anywhere, and it collapses on itself. There's only 1 degree of freedom. It's this one. It's just the size parameter. And it goes back and forth, back and forth. This is the Miura Ori. Okay? And you can see that globally, if you kind of stand back far away and look at it very vaguely, it is a negative Poisson ratio behavior. Yeah? I'm approaching 2 points toward each other, and all the other points actually collapse in the same way. Okay? So that is the beautiful Miura Ori. And slide, please. you can make maps out of this. And as you saw, there's 1 degree of freedom, and also negative Poisson ratio behavior. It turns out that the negative Poisson behavior is very intimately connected with very few degrees of freedom in the deformation. Okay, and also hyperbolicity, I shall come back to that. So you could buy this kind of thing in Japan. I don't know if they're still manufactured, but it doesn't matter because the original application of Miura-Ori, I told you that Mr. Miura is an aeronautical engineer, he's a very old man now, was to an artificial satellite which Japan launched in the 1990s. You know, one of the challenges of satellite technology, artificial satellite technology, is, say, a solar panel or antennas, which once in orbit has to be expanded into as large an area as possible in order, for example, to receive the sunlight or in order to have the good cross-sectional section towards the Earth and so on. But while you put it in the rocket, you have to compactly sort of package it in some space, right? So you have to have something that is very, very tightly packaged, expanding in space. How do you do this? The usual way that people have been doing is very bad because you know what happens? So the satellite goes into space and then it's in orbit and it starts expanding this and it goes clack, 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 and it gets stuck because there are so many degrees of freedom where failure can occur, where it can get stuck, and then you have lost $1 billion. But Miura-Ori is really a great idea, and it has been tested on Haruka, this satellite, because it has only 1 degree of freedom. So when it starts expanding, all you have to do is to grab two pieces and just pull them apart. And mathematics says that it's absolutely impossible to get stuck. Yeah? And if it possesses you to fold it back again somewhere, for example, if you're going on a mission to the moon or something like that, then you can just push them together, and it completely automatically falls back in itself thanks to this mathematical property. So it has been tested on Haruka. Okay, so I would like now to experiment with interesting things. And can we have the alternative camera, please? Miura-Ori, as you saw, is negative Poisson, but it actually does depend on direction. So we are now entering the more interesting and rather trickier domain of anisotropic elasticity, material response. So it depends on the direction. So here is the first experiment. Those two squares I cut out from a single sheet of paper, printing paper that I found next to my office at Stanford University. There's nothing wrong about these. And then I put them together, and I clamp one edge of these squares, okay? All right? And then if I support them like so, they remain stuck, right? And they stick together. Of course, because they're made of the same material. Not only that, they're actually twins. They are made of the same material, so they sag the same way under gravity. So of course, they curve the same way, they get stuck. Yes, nothing surprising. But now, when I turn them over, they separate. So on this side, they get stuck. On this side, they separate. Magic, but which you can do with any sheet of paper yourself. I'm going to tell you what's happening, but it's stuck. But that's not all. This is the separating side, okay? Now I'm going to let the clamp migrate to the next edge. So instead of supporting the paper on this side, I'm supporting on the next side. Now this used to be the separating side, but if you support them on this side, they stick together. But the other side, which used to be the sticking side, now they separate, okay? So what is going on? This has to do with an anisotropic property of paper. You see, a sheet of paper, can we still keep the camera, please? The sheet of paper has some anisotropy, direction dependence. It's not visible, yeah? But some of the fibers might be running this way, not this way. So in order to illustrate this, I'm going to do another experiment with the same camera. It's probably the first time in the long history, I don't know for how long PCMI has been going on, maybe 30 years or something, 35 years. In the history of 35-year history of PCMI, it's the first time that the speaker, lecturer, brings in toilet paper into the lecture, yes? So here is toilet paper that I harvested, by the way, from that corner. Okay? Yeah, there, a moment ago. And when I try to tear it along in one direction, it tears very, very smoothly and very straight, like this. But if I try to tear it in the perpendicular direction, I basically can't tear it. It goes all over the place. I'm trying to go as straight as possible. You see, it goes zigzag, zigzag, zigzag. Yeah? So there is an anisotropy because of the invisible fiber direction, which you can detect by doing this. By the way, I couldn't help noting that this Park City, Westgate toilet paper, yeah, tears more easily lengthwise than across. So we should really think about this problem. Okay. Can we have the slide, please? So there is anisotropy, so direction dependence. This is very interesting. Okay. Now, let's go back to geometry and then wrap up the whole thing. Here's a funny question which motivated lots of people. I forget, maybe 30 years ago or so, maybe 40 years ago or so. Let's say you have a big sphere. By sphere, I mean a two-dimensional spherical shell. Okay, only this sort of shell part, not inside of free space. Okay, and can you take that and then put it inside a small sphere, okay? And the answer is, of course, yes, you just squash it. Can you do it isometrically? That is, without changing the metric, while preserving the distance all over the place. Can you actually put it in a small space? By the way, this problem is trivial if instead of a sphere, you take a circle. Yeah, circle in 2D. Can I put it inside a small circle? Yes, I just wiggle it, and it's isometric. Yeah? I didn't change any length along the circle, and then you actually wiggle it enough in order to put it inside. Is that okay? But for a sphere, it's interesting. Now, the answer turns out to be no, because when you try to squeeze a sphere, you're bound to do something like that, right? You press and dent. But when you dent, it changes something called the Gaussian curvature. Many of us know this. Some of us may not know. It doesn't matter. It is an invariant of geometry, and it measures how curvy your surface is. And it turns out to be invariant under isometry. Okay. So when you dent, originally the sphere had positive Gaussian curvature, to be precise in 2D, 1 over radius squared. But along, you see, you created something like a crater. And along the crater, you are having some kind of ridge along which the Gaussian curvature becomes 0. And that's not allowed because then it's not isometric because the Gaussian curvature changed. So if you like, curvature gets in the way of doing this isometric embedding into a small space. Okay, so that's not allowed. But, curvature, if you learned how to compute curvature in differential geometry, involves two derivatives, second derivative. So here's a crazy idea. Can we actually do this isometric embedding, the deformation of a sphere into a small space, by using surfaces that have only one derivative, first derivative, but not two? And then you try to do it. And if I manage to do this, and you're going to come and complain, oh, you can't do this because Gaussian curvature gets in over there. I say, well, what Gaussian curvature? You can't compute the Gaussian curvature because you don't have two derivatives. I'm giving you only one. This sounds like quibbling, but actually the greatest minds of our generation, such as Nash and Gromov, managed to do this, prove the existence of isometric embedding of this kind. And more recently, a French team led by Borelli and Thibert managed to have a concrete realization of this embedding. And that's a 3D printed version of this. And when Thibert came to see me and showed me that picture, so you see, it's very, very strange. You first twist the whole sphere, and then along those corrugations that happen, you zoom in under microscope, and each corrugation is lined with more corrugations and more. This is kind of nested structure. And I said, I have seen this before. That's Miura-Ori. Can we have the camera, please? Here is a pair of straight glasses that Dana very kindly provided me with. So straight, not the flared, but straight cylinders. And take a sheet of paper. I'm going to show you one buckling. You remember this buckling? Yeah. But one example of two-dimensional buckling, which is very, very little studied, and in fact, almost unknown. But it's a very beautiful one. So what you do is you take a sheet of paper and put those two cylinders against each other, but with a little gap in between, and start rolling the paper around those two, okay? And having rolled them, keep them tight, I twist one glass against the other, like so, and then squeeze, okay? And when I unsqueeze and see what happened in the middle, you see this rather beautiful pattern. That very beautiful geometry is entirely determined by one dimensionless parameter, that is, how far the gap between them is over the diameter. That single parameter gives you this geometry, yes, on both sides. And you see if ever saw it, that corrugation pattern is the same corrugation that we saw on that 3D printed model of the Borel bear and so on. And no wonder, because what did I do? I put, with the help of those two glasses, this paper in a tight spot. And I asked nature, can you actually put this as cost-effectively and as non-violently as possible into a small space? And nature had to do something because it couldn't do it isometrically purely. So it has to actually concentrate its cost along singularities, and those are the folds. Yeah? So nature actually solved the problem for us of isometric embedding. Yes? And that's exactly what that thing is. In other words, we, of course, admire the intelligence of Nash and Gromov, who proved the existence of such a thing, and then Borel-Tibet, the imagination of working at a concrete algorithm for this. But we could have actually asked nature to do it for us. Okay? So that's the first thing. Now, the second thing, which is related to this, is this beautiful, can we have the camera, please? Origami, which was designed also maybe a little later than Muraori, in 1980 or thereabouts, by Momotani, another aeronautical engineer. And this is made of a single sheet of paper. I'll show you what it is. Very large like this. And I started folding it on a long airplane flight, and it was maybe 10-hour flight or so, and I brought in this large sheet of paper. I sat down and started folding it, and my neighbor looked really nervous. And then in the course of the flight, somebody brought coffee, and they spilled it, so I think there's a coffee stain here. So what it is, so Momotani carpet, it's called, is as follows. It's made of a single sheet of paper, okay? And when I pull in one direction, what do? Whoop. It expands in all directions. And what's happening on the other side is dual to what's happening in front. Yeah. So, and this is negative Poisson ratio behavior as well. I'm pulling in one direction, and it's expanding in all directions, as was this one. Okay. So this is really interesting, but let me digress a little bit. It's not only a very beautiful origami, which has, from a single sheet of paper, realizes negative Poisson ratio behavior. I mean, paper doesn't usually have elasticity, but I gave it elasticity. It's really elastic in the more common sense of the term. When I pull and then release, it just bounces back. It's bouncy, bouncy, bouncy. Yeah? So this is a way of folding an otherwise just rigid sheet of paper and turning it into something like a rubber. Origami does this. Okay? And this is really a very, very nice, nice pattern. And I'd like to mention one application of this. I have a great friend, Manu Prakash, who's a MacArthur Fellow at Stanford, and he's a very, very imaginative engineer, and he's much younger than I am, but we have been the best of friends. And recently, and he does something amazing. He calls it frugal science. So his idea is that you take some very, very important piece of technology, which is expensive, for the good of humanity, and then using your intelligence and imagination, make a radically cheaper version of the same thing, or even sometimes that outperforms the conventional one by a factor of 1,000 or something like this. And that's called frugal science. And so we have been the best of friends, and we talk about this a lot. And one day, a while ago, he had a really very difficult health issue, and he kind of almost died, actually. And he was hospitalized in the Stanford Hospital, and I went to visit him. And he told me that one of the really most unpleasant experiences during this was that they stuck a tube down his throat to feed him. And then it was really hard, and of course it was necessary. And then we began to discuss, well, suppose that we make such a tube with this Momotani carpet, but it's periodized into a cylinder. Okay, so origami has lots and lots of strange corners where food will get stuck, and so that's not good. But we have to modify the structure. But nonetheless, negative Poisson ratio tube, okay, with that. So what happens is that when you then put this tube down your throat, it's going to be in compression. Right? So it's going to shrink. So it will go down very, very nicely because it will be so thin. And once its tip has reached your stomach, and you know where you are, you just tug, and you are going to stretch, and then it immediately expands and hugs the inside of your esophagus very nicely and so on. So it will be a really much nicer way to deliver things like this. And there are some other ideas about stent that you can put in your blood vessels and so on, which come from this. But this is still in a work in progress. Can we have the slide, please? So it's time to wrap up all of this. Here's an example of Miura-Ori, who has been getting the star billing so far, that photo. And let's simplify everything. This is the simplest of Miura-Ori. Let's say that it consists of, if you like, parallelograms. In fact, rhombuses, so parallelograms with all the sides are the same length. And then you just use them as panels and then put them together. This kind of Miura-Ori then has two parameters, angular parameters. One of them tells you the geometry of the design of Miura-Ori, and the other one is dynamic, in what state of sort of compression it is. So alpha is that angle. So alpha is that corner angle. If alpha is, for example, 90 degrees, each panel of Miura-Ori is simply a square, okay? And if alpha it becomes smaller, it becomes long and thin. Theta is the angle between two adjacent panels, okay? So when theta is almost 180 degrees, the whole thing is flattened out, and if theta becomes smaller, everything becomes compressed, okay? So those are the two parameters. And in that configuration and for that Miura-Ori, it's actually not too difficult to compute the Poisson ratio, which is equal to 1 minus that expression. Now, if you remember anything about sine, it's between 0 and 1, or minus 1 and minus 1. So you are subtracting something that is greater than 1 from 1. So that number for any alpha and theta is negative. So you have negative Poisson ratio for the Miura-Ori, which we already saw. But there's something more. You see, by playing with alpha and theta, I can make that Poisson ratio hit any pre-assigned negative real number. Okay? So that means that not only is Miura-Ori a negative Poisson ratio creature, but it is the universal negative Poisson ratio creature. For any negative number that you care to mention, I can actually realize that negative number as Poisson ratio of my Miura-Ori. You are going to complain, well, what about the theorem that I made a song and dance about, that the Poisson ratio should be between minus 1 and plus 1/2? But that was for isotropic material. This is very, very anisotropic. There's one direction and the other direction. So for anisotropic material, there's a lot more freedom. But there's even better thing coming up, which we discovered, which is that you remember the buckling metaphor? Let's do the buckling for a 2D membrane. So what do we mean? Ideally, what you would like to do is to take a two-dimensional surface, and then at each point apply a homogeneous and isotropic compression. Yeah? This is very difficult to do. So some people say, what about just pressing on but then the boundary effect becomes far too dirty. So maybe you can do a thermal expansion, thermal contraction, things like that, or wetting and so on. But anyway, theoretically, you can do this. And so when you do a two-dimensional, completely homogeneous and isotropic buckling, well, for a while, the entire sheet shrinks elastically in its own plane, but at some critical load, it can't take it anymore, and boom, it deforms into the third dimension. And that deformation pattern turns out to be Miura-Ori. That is the lowest energy deformation mode for the compression, for buckling, two-dimensional buckling. So again, we could have actually asked nature to invent Miura-Ori instead of waiting for Mr. Miura to invent it. So Miura-Ori, I cannot emphasize enough, is the simplest and universal model of negative Poisson ratio behavior. At this stage, I realized something. You know, we have been very, very careful and very intelligent and very inventive in doing this and that and design. But there is actually a much easier way of realizing negative Poisson ratio behavior. Just crumple a sheet of paper. Main camera, please. Always start from a sheet of paper. And then and when I try to uncrumple it, it expands in all directions. That's negative Poisson ratio behavior. Well, of course, because I made it that way. I just crumpled it and I compressed it in all directions, more or less isotropically. And so when I uncrumple it, it just expands. Now, it's true. I'm going to be very, very honest with you before you start criticizing. If you take a bird's eye view, as I'm showing by camera, it looks like it's expanding in all directions. But if you look at it sideways, when you crumple, it actually became fatter, right? Because it was a zero sheet of paper. But when you crumple, it became thicker. But on the other hand, for any pre-assigned epsilon, I can, by having a large number wave number, you can crumple this and constrain the crumpling between this gap of epsilon. So if you take the attitude that finite approximation error is allowable, then for any finite approximation, it's fine. So for all intents and purposes, for all applications, this is negative Poisson behavior. Okay? So this is really a remarkable thing. And look, this looks pretty random, right? True, there are lots and lots of properties that are hidden here. For example, that sort of alternating sum being 0. But modulo those, this is as random a picture as you can imagine to human mind. Can we have this slide, please? And this also, on average or large scale, is homogeneous and isotropic. And by construction, it's negative Poisson. Just by crumpling the sheet just by doing the random thing. Instead of trying very hard, working very hard to design something deliberately, you just do things randomly. So here's a bold conjecture in bold typeface. We used to believe until recently that the negative Poisson ratio behavior is really freakish. It maybe didn't exist, and if it existed, you really had to work hard to realize this. But no, I have a feeling that a random structure in the universe tends to have negative Poisson ratio behavior in the majority of cases. This is something that you can. It's time to conclude this entire lecture. And I'm going to inflict some speech on this, on you. Okay, so we, of course, operate as professional scientists, so, the budding professional scientists, some of us are retiring professional scientists. Anyway, professional science is a big, big industry. And we expect that the science happens in special environments. We and the general public, labs, institutes, internet, that's where the information is usually culled in those, and then libraries, classrooms, and of course we have to obtain big research grants, especially in experimental sciences, and then in order to do so, we have to submit cutting-edge proposals. I don't like this language, cutting edge. It really hurts. And anyway, and these are all supremely important because that's where we expect new science to come from. Yes, that's what we do. That's our life. All those things. So, and you believe that, okay, so when labs close and institutes are down and the internet is off and so on, science stops existing. Yeah, and we go on holiday and you don't think. But there's something or somebody who's practicing science 24/7 everywhere in the universe, and that's called nature. Even if you are not looking, it's happening. So you might ask, against this background, why, Tokieda, are you playing with paper? Yeah? In guise of a response, I'd like to share with you another present, a very little known passage of Aristotle. Aristotle wrote lots and lots of books in scrolls, and one of them is called De Partibus Animalium, on the parts of animals. And in this, he tells an anecdote, and that's Deals und Kants in the lower right corner, 2289. If you look on the internet, you'll be able to see the actual sort of manuscript sources of this. So in there, Aristotle tells a story of Heraclitus. Have you heard of Heraclitus? He's one of the Socratic philosophers who said, "Panta rei," everything flows, and so on. A very clever man. And he was a big, big shot. Okay, so he was, equivalent in those days of, say, some senior member of the PCMI, and he was a world star in science. And so in those days, he was very famous, and two young people wanted to visit him. And so they came to him and expecting what then? Head of a huge laboratory, maybe in those days a person with a white beard, and maybe at the console of a supercomputer coding something huge and so on, or maybe lecturing to an adoring crowd of 1,000 disciples in an auditorium, whatever. Yeah. So, but when they came to Heraclitus and saw him, he was completely different from what they had expected. Okay, and this is Aristotle speaking, and my free translation. In all natural phenomena, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus. But when they entered and saw him in the kitchen, warming himself at the stove and playing with the children, they hesitated. Is this the Heraclitus that we want to see? But Heraclitus said, "Come in, don't be afraid. There are gods even here. Enai garkai en tausa theus. There are gods even here." It has been a great pleasure and privilege to address this very friendly audience. And I would like to single out to thank especially Rafe Matseo and Dana Wihil for their very kind hospitality and invitation. I would like to wish you a very good life in science. Thank you.